Two people coming, so already start. So what we did on Wednesdays, like we constructed this cube complex, or these cube complexes where groups of birational transformations in any dimension act upon. So what I would like to do today is, okay, we would like to use these cube complexes to, yeah, it's always good, like if you have several mini courses, if you do a bit of bridges between those. So what we will do, the main goal is kind of like to make the connection that Evgeny already mentioned yesterday of these cube complexes to the motivic invariants. Just so we see kind of like this motivic invariance very naturally appear. Like already in the construction, kind of like we had this factorization given by just looking at the open subset that embed into it. It's kind of like similar ideas, and so it's no surprise that this is closely connected. And then if we have time, maybe we'll have a brief look at some variations, or at least one variations of our cube complexes, like mostly the blow-up complex. Just to give a bit of outlook, or also kind of like encourage everyone, like if you need to prove something in certain direction, just try if you can adapt the cube complexes a bit, and maybe this can be, it can be fun and sometimes leads to something. But okay, let's start to this connection to the motivic invariance. So what we will need or use is kind of like a general construction that works for cat-zero cube complexes. And I think it's like interesting in itself, and I also thought it was interesting for groups of birational transformations, because it's kind of like a way to construct quotients of groups that act on cube complexes. So I want, okay, so we need one lemma about cat-zero cube complexes, which I will not prove. It's not so hard to prove, but you also then again need some facts, and then we can also just assume the lemma. So if L is a cat-zero cube complex, and alpha and beta two paths in the one scale, well, okay, let's make a convention for today. Like if we look at a path in a cube complex, for us it will always be in the path in the one skeleton, so a combinatorial path. Let's make this connection today. Path in a cat-zero cube complex is a combinatorial path. Okay, so if we have two combinatorial paths with the same endpoints, okay, then we can transform one of the paths into the other by certain moves. So we can transform alpha into beta by adding or removing backtracks. And by flipping squares. So I should tell you what it means to flip a square. I mean, adding and removing backtracks is clear, right? Like if you have a path that comes, and then at some point you just have a path that goes and it goes back, then we can just, either we can add such a thing or we can remove it. A pretty basic changement of path. So that's adding, removing backtracks, and flipping squares. This means if we have a path that comes here on the one skeleton, and then it continues. And if we have a square here, then we can just move it to, maybe, let's use some colors. Then we just move it to this side of the square, the big square. And the lemma tells us that actually with these two moves, you can transform any path into another path. So if you have two path alpha and your path beta, then you can just transform alpha into beta by doing these two moves finitely many times. Well, I mean, yeah, it corresponds like here you remove one hyperplane and then the other one, and here it means you first remove this one and then this one. No, it has nothing to do with geometrical flip, nothing. Flipping is maybe also a bit of a multi-layer term in mathematics, or not uniquely defined term. Yeah, no, it has nothing to do with flips in birational geometry. Okay, how to show it? Like you can first, to show it, usually you should first show that you can transform an alpha into a geodesic by doing these kind of moves. And then in the next step you show that that any two geodesics can be transformed into each other by these two moves. Okay, so this is the lemma that we need. Now let's make a definition. That's like from algebra, from geometric group theory. So this is if gamma is a graph, then we define the right-angled Artin group given by gamma. So is the group, call it A gamma. So it is the group generated by so just abstractly take as generators the vertices of gamma, or the vertices. And so we take the free group on the vertices, and now we take the following relations. So we say that we take the commutators, so let's say U, V, U inverse, V inverse is equal to 1 if U and V belong to an edge. So if U and V is an edge of gamma. So it's a free group with certain commutation relations, and this is described by this graph. So the basic examples, like there's two extreme examples. Like one of them is if gamma has n vertices but no edges. Then the right-angled Artin group of this graph is just the free group on n generators. Yeah, you have like n generators, no relations. Good. And then the other case, the other extremal case in some ways is if gamma is a complete graph. And this is the case we will be in today when we look at our example. Then, so basically we take n with n vertices. So So we take n vertices, we connect all the vertices with each other. Then this is just the free abelian group on n generators, right? Like because all the generators commute with each other. Okay. Now back to cube complexes. So let L now be a cat zero cube complex. And G a group that acts on L by isometries. And now we assume that it preserves the given orientation. Now, this is just the same as saying if G acts without inversions, then we can always find invariant orientation. Just choose one, and then we take all the orbits the same orientation. So basically, the fact that there exists an orientation that is preserved by G is equivalent to saying that G acts without inversion. But okay, we assume it acts without inversion, and we have a given orientation. And what we do now is we define a graph. And so this gamma we define the following way. So we say that the vertices of this graph are just the G orbits of hyperplanes of our cube complex. Okay, so G acts on L, so in particular it also acts on the hyperplanes of L. And now we take these G orbits of these hyperplanes. So these are our vertices. And now we say that two of these vertices are connected by an edge. If we find a representative of like a hyperplane in one of these G orbits of a hyperplane in one of these G orbits and a hyperplane in the other G orbit that intersect transversally. So we connect two vertices. Okay, so we have here one G times H1 and G times H2. By an edge. If there exist hyperplanes so a hyperplane D in G times H1 and E in G times H2. Such that D and D are transverse. So basically we have here being transverse means we have here one hyperplane that's given by this parallelism class of edges, and then the other one that intersects. So there exists a square basically. Yeah, there has to exist a square where these two edges define one hyperplane and these two edges the other one. Okay. Okay, so we have these orbits, and now if we have an oriented path alpha, in L. So now what we do is we label now this path alpha by the hyperplanes it transverses, but like only we take respect like the orbits. So So each of these orbits has it's kind of like a label attached. So I don't know. We have the path alpha that goes. And then we have maybe here one hyperplane. I don't know. Let's call it A, but then in the same orbit, like that A is just denotes the orbit. So there could be like this one here. I don't know. It's again one A, and here's another one A because they might in the same. It's not the same hyperplane, but they are in the same orbit, and then it has another orbit that is intersected, orbit B, and right. And then what we do is we look like a box over here. So the label of A would be A, and then after it goes over B, and then here we would have to see now what you take into account is whether it goes from negative to positive or from positive to negative. So if it goes from negative to positive, we make A, and if it goes from the negative side to the positive side, we make A inverse. And yeah, this is well defined because G preserves orientation. So yeah, we have to be a bit more precise where this goes through, right? Like so here, let's say this one is the positive side, and then this one is the positive side, and B, and this one is the positive side of B. So okay, here it goes from positive to negative. It goes again from positive to negative, again from positive to negative. So I have A, B, B, and I don't know, we have C, and then maybe it goes from negative to positive. So we have B, and we have B inverse, etc. So we have labeled to each path. Okay, so we just label alpha on how it goes through the hyperplanes, but like the orbits of hyperplanes. Like if you would just look at the hyperplane, right, like it has to go, once it goes from positive to negative, it's in negative, so you can only go from negative to positive again. But that's not the case because it's like kind of like the next hyperplane that it crosses is a different hyperplane than before, but it's in the same G orbit. Okay, so let's write it down. We can label alpha by a word. Okay, and the word is now in the vertices of our graph. So and the inverse of it. V gamma and V gamma inverse, given by the oriented hyperplanes. Crossed by alpha. Okay, and yeah, so basically, now what we do is we fix now vertex V in our cube complex. And now what we claim is that the following map, so the map theta that goes from our group G to the right-angled arcing group over our graph gamma, that maps G to the label of the path from B to G times V. So the claim is that this defines a group homomorphism. that if you take an arbitrary, if you take another v, yeah, it's just conjugation, exactly. Yeah, exactly. Up to conjugation, it doesn't depend on the choice of the vertex v. I did not draw C. I should actually have, I didn't draw it carefully, yes. So here, what did I draw? I did A, B, B, C, so okay, this should maybe be C. Let's maybe be a bit better in my drawing, yeah, that's true. A terrible drawing. So let's say, okay, A, B, B, and then it goes over C. So let's say here, and this is the positive space. And then after we said B inverse, so the next one would be B, but this time it goes from negative to positive. Then we stop here. Yeah, now it's, sorry for just randomly drawing hyperplanes and colors. Good, so now let's prove that this is a this is indeed a homomorphism. So let's prove this. Okay, first we have to observe that it is well defined. So it does not depend on the path we choose, right? Like if we choose two different paths from V to GV, they should give us the same word. So if alpha and beta are two different paths, from V to GV. Here we have some path alpha, GV. Here we have path beta. And now we can apply our lemma from before, is that we can actually transform alpha to beta just by removing backtracks and by flipping squares. And then we just have to see that this will not change the image. Okay. By our lemma, we can transform alpha to beta by adding or removing backtracks. And by inverting squares. And both of these moves do not change the image in the right-angled arting group. I mean, okay, if we add or remove a backtrack. I mean, it's clear, so if we have a path coming here, and then we just have some backtrack here, and we go back, and then we continue here. So basically here, I mean, it's exactly the same hyperplanes that we cross in one direction and then in the other. So first, this just gives us a corresponding word, and then we have here, okay, let's just have two maybe. Then we have here A, B, and A, B, and then we have B inverse, A inverse, because we just go the other direction, so this doesn't change the word. And also for flipping the squares, so if we have a path that comes here and then makes this one, and it continues here. And now if we can flip the square here, so if we have a square here and now we change it to this new path here, then we see the hyperplane that is crossed here, or like the A and this one the B. This means they are transverse. So this means the corresponding vertices are connected by an edge. So these two words commute in the right-angled darting group. So here we get that well, we have the word AB up here, and then the new path gives us the word BA, and we know that in A gamma we have AB is equal to BA. Okay, so it is well defined, does not depend on the choice of path. Then we can see, okay, then we have to see that it's a morphism, or a homomorphism. So if we have G and H, two elements in G, and alpha is a path from, okay, let's write it as maybe V to GV. Okay, let's write it just as an interval. It's a path from V to GV. And beta then a path from V to HV. Okay, and now what we can observe is that the label of beta is the same as the label of G times beta. Right? If we translate our path by an element in G, this does not change the label because, I mean, the label is given by G orbits, or G orbits that are crossed. Okay, so and then G beta is a path from GV to G times H of V. Okay, so we can just this now we can concatenate. So we see that the beta of G times H, well, it's just the label of take alpha union G times beta. And this is now the same as the label of well, we first go the label of alpha and then the label of beta, so it's just the label of alpha, like times the label of beta, of G beta in the arting group. But this now is exactly the same as the label of alpha times the label of beta. Because multiplying by G does not change. So we indeed have a homomorphism. I think it's actually quite pretty construction, like kind of like how to get quotients from these actions on cat-zero cube complexes. Of course, like you have to verify that this homomorphism is not trivial, so that's maybe the trickier part in general. The observation was made by Anthony Genova. Remember when he explained me once this construction, and then you always try to think about what does it mean in our cube complexes, and I thought, like, oh no, that's exactly what Evgeny Schindler and Lin did. And then after I realized it's even potentially stronger, although that's not clear. Maybe just a remark for the group theorists. In case that G does not preserve an orientation, we still get something. Then we get a homomorphism not to a right-angled Artin group, but to a right-angled Coxeter group. So basically, we just care whether it walks over the hyperplane or not, and we don't have an orientation anymore. So it's just like a right-angled Artin group, but every element has order 2 in addition. Write this down: if G does not preserve an orientation, then similarly, get homomorphism to a right-angled Coxeter group. Okay, but now let's go back to groups of birational transformations, because that's why we are here. So we have seen that this group of birational transformations, Urech, acts on some cat-zero cube complex isometries, and the vertices of cube complex were given by equivalence classes of pairs, of marked pairs, I phi, where phi is a birational map from A to X. And we saw that 2 of those were equivalent if the corresponding markings induce a pseudo-automorphism. And now the edges, they were given by just adding or removing hyperplanes, hypersurfaces. So the edges, we had like I phi was connected to by an edge to A, where we remove some irreducible hypersurface H, and we just take the marking of A restricted to H. Okay, and we've seen if we have like such a triple and we have hypersurface H of A, then this defines us a hyperplane in the cube complex. And we have seen that two such triplets define the same hyperplane. B K define the same hyperplane if and only if K was not contained in the exceptional locus of psi inverse psi, and H is just a strict transform of K under phi inverse psi. Okay, and now let's see also what does the action of Urech do to the hyperplanes. So write this here. So make the following observation. So if F is a birational map of birational transformation of X, then F maps the hyperplane given by A phi H, the hyperplane given by A F phi H. Right, like if you have here the vertex given by H. Now this is mapped by F to A F phi, and this one is mapped to A without H, and here we have F phi restricted to A without H. So it's basically just the one where we remove H from. Okay. Good, so now we can, with this observation, we can now describe the orbits of hyperplanes, so of hypersurface hyperplanes. So two hyperplanes given by X phi and H, and X psi K, they are in the same Urech orbit If and only if there exists a f in here x such that k is not contained in this exceptional divisor of phi inverse of f of this one. And phi inverse f of psi of k Urech transform is equal to h. Is that? Did I write it correctly? Yes, so if we have f such that when we apply f here, then we get the same hyperplane as this one, and this is exactly saying that. Okay, so we see in that case, this means there exists a birational map, so phi and psi and f, these are all birational maps of x. This means that there exists a birational map that maps of x that maps k to h. This is by definition, this means that k and h are Cremona equivalent. How did you define it yesterday? How did you call it yesterday? Different word, but okay. Classically, it's called a Cremona equivalence. The pairs are birational. Yeah, there are a dozen of papers maybe about the Cremona equivalence of varieties. Okay, and Cremona equivalent means in particular that they are birational, of course, but it's actually much, if they are divisors, so if they are of codimension 1, being Cremona equivalent is much stronger than being birational equivalent. There is papers by Mella and other people where they show actually they are if you have a given divisor, there are kind of like infinitely many non-Cremona equivalent embeddings of this divisor into Pn. Yeah, so they are birational equivalent, but not Cremona equivalent. If you go to codimension 2, then all of them are Cremona equivalent in Pn. But okay, what it does not mean, and I think that's an open question, that's the one that FKD is about to prove in dimension, or proved in dimension 3, and it's open in higher dimensions, is if this phenomenon also applies to divisors that are contracted by some birational map, right? It could be that if you have that for birational transformations, it could actually be the same. So if they are contracted by a birational transformation, and it's inverse, and they are Cremona equivalent, that's if and only if they are. Right, that's okay, in this case, we will see a priori it's much stronger, but we will see it's unclear whether it's actually stronger or not. And now, okay, with this observation, we can now apply this theorem, observation about constructing quotients of groups acting on cat-zero cube complexes to this situation. So if we have f in here x, a birational transformation, such that well, the irreducible components of pure codimension 1 of f, so this is just h1 to hk, well, L maybe, and the exceptional irreducible components of the exceptional locus of f inverse. Pure codimension 1 is, let's say, k1, km. Okay, so if there now exists hi, so if one of these hi is not Cremona equivalent, to any of the kj, then the homomorphism that we constructed before theta that goes from Urech to well, the corresponding right-angled arcing group satisfies that f is not in the kernel of this homomorphism. And to prove this is basically what we do is we fix the vertex. We fix some vertex. B as our base vertex, and for example, like just take X identity. That's the most natural one. Cube complex. Then if you look at the path from V to FV. Well, okay, here we have X identity. Now, what we do here is we remove all the hyperplanes HL, right? We have until we have here U identity, which is the same as UF, and here we just add all our hyperplanes KL until we get to XF, right? So here we see exactly we cross all these hyperplanes defined by X identity and the HI. Here we cross all the hyperplanes given by XF, KS, let's say. So this path from V to FV crosses the hyperplanes given by X identity HR and XF KS, right? And it crosses these hyperplanes with positive signs. And this one with negative signs. Or how did I define it before? Yeah. Well, no, wait. Here we go from up to down, and then from down to up. Okay, I don't know. Like it's just the inverse signs, right? Okay, but now we see that here we have the hyperplane that's given by X identity, and we take our HI, and this cannot be in the same orbit as any of these hyperplanes, because this HI is not Cremona equivalent to any of the KL. Right? So none of the hyperplanes X XF K KS is in the same Urech orbit as is in the Urech orbit of the hyperplane X identity HI. Okay, this means that the corresponding homomorphism, theta f, is the image of this homomorphism is not zero. Yeah, because we have here some label that does not vanish here. Okay, and then also again, like we see, of course, as in the with the invariant of Schindler and Lin, if we have G in Urech that is conjugate to some that is pseudo regularizable, it's conjugate to a pseudo automorphism of some model y of x, then f fixes a vertex, the G fixes a vertex. In our cube complex, and then this implies that P is in the kernel of theta, as remarked before, because like if it has a fixed point, I mean, then we can just take this one as a base point. It's just given by conjugation, and of course, it has to be zero. So again, we get that. So if f is as in the theorem, then f is not in the group generated by pseudo-regularizable elements. And then, yeah, I mean, yes, okay. And then the question, of course, is whether, or a difficult question, is actually whether such a f exists or not, right? But that's what we learned in the mini course by Evgeny, that actually they exist. So for n equal to 4 for all fields of characteristic 0, and for n bigger or equal to 3 for most fields, or many fields, I don't know. Such examples of f. Exist. And yeah, but okay, here to know that such a f exists, what we observe is that there exists one of the hi that is not birationally equivalent to any of the ki, right? So we don't use the kind of like possible stronger version of this field. It's also not so easy to show that two hypersurfaces are not Cremona equivalent. I mean, the easiest way to show this is to show they are not birational, but then harder. But also, it's not clear whether it's stronger. So just to make the bridge, so our construction gives a homomorphism so from Urech to, yeah, okay, that's, I mean, I'm not too detailed about it, but of course, like we've seen, our cube complex C0x is just one big cube, right? Like it was just like, take finite subset of vertices, they're always contained in a cube. This means if you take any two hypersurfaces, they're always transverse. So in our case, our graph is not very interesting, right? It's the right-angled Artin group will just always be the free abelian group. So our homomorphism basically goes from Urech to the free abelian group. So it's our theta on equivalence classes of Cremona equivalent hypersurfaces. And then, of course, from here, we can just take the quotient by saying two of them are the same if they are birational. So we get mapped to, to this Burnside ring. And if you take this quotient here, you just get again a motivic invariant C. And it's really not clear if maybe here the image of theta like is indeed like, then it's just the isomorphism here to Burnside K-1. That's the work, the forthcoming work of Zika, Schneider, and Schinder. Yeah, so the hope was, of course, that in dimension x equal to 3, where this one is trivial, this invariant is trivial over the complex numbers, then maybe this one would not be trivial, but exactly in this case, they show that it's trivial as well. So, but it's also possible that actually in higher dimensions, it's exactly the same. So it's maybe just, yes? Yes. I mean, that's the, yeah. I mean, that's like the, you just take a path from, no, I think for this you would have to make other constructions. So for us, it's really just for Urech because we have this group actually, the cube complex, to work a bit to, yeah, that's not obvious. Yeah, that, I mean, a priori, I would say it's always, a priori it's always 0. Like, okay, if we know that this one is 0 by the work of you and Lin and Zimmermann. So, and for points, I think for points on surfaces, they are Cremona equivalent different only if they are isomorphic, I would say so. Yeah, maybe, not so clear. Maybe, maybe it could work. But then again, like also for, right, like, okay, for example, if it's the Cremona group, then we know over perfect fields, it's generated by involutions, so it has to be trivial. It cannot go to Z. We don't get a homomorphism to Z. But okay, I think there's maybe, for example, if you look over for this question that you asked, if it is whether it's generated by regularizable elements or not. Maybe in some cases one could. So I think, okay, like that's maybe something I would like to advertise. It's kind of like, okay, I think might be worth thinking about it if this construction can be used in other ways. Like we thought about it a little bit, but not massively. So I think like one thing is really like looking also in the surface case with the blow-up complex, and then considering like certain varieties over non-closed fields, see what you get. Also, one thing that's interesting is like now we looked at the operation of Urech, like the whole group Urech on the cube complex, but you can also look at the smaller subgroups, and then of course you have fewer orbits, and so you can, if you want to construct quotients of certain subgroups of the Cremona group of groups of birational transformations, you could maybe then there's some hope that you get new methods of constructing quotients, which is in general always interesting. For example, like already in dimension 2, it is open whether every finitely generated subgroup of the Cremona group is residually finite. And maybe, I don't think one can answer this question with the blow-up complex. Tried a little bit. I didn't try super hard, but maybe for some classes of finitely generated subgroups, this could give this gives you new methods to construct quotients. Residually finite means that for every group G is residually finite if for every element G in G you find a homomorphism from G to some finite group H, such that G is not contained in the kernel of this homomorphism. So basically, like if you take the intersection of all the normal subgroups of finite index, it should be empty. And it's something that's been it's studied often in geometric group theory, and it's kind of like equivalent to saying that your group injects into its profinite completion. And it is known for linear groups. That's like a typical example. Linear groups satisfy this property, like that you have every finitely generated group is residually finite, and you can show it for automorphism groups. And then if something that's true for linear groups, for automorphism groups of varieties, you would hope it's also true for groups of birational transformations, but it's open. So maybe these kind of questions, like all the questions that involve making quotients of groups of birational transformations. Okay, but I'm going over time. I wanted to, technically it's already part of the questions period, so it's I wanted to say something about variations of cube complexes, but maybe let's not do this. There's in 2 weeks, there will be talks by Anne Lanchou, and she will talk about it. Thanks a lot for